Okay, what I'm going to do in this video is have a look at the January 2019 Physics Unit 1 paper. So we're going to start off with question 1, obviously. So we've got this slinky spring, and it's basically being used to show a longitudinal wave. So what we want to think about at this point then is, what does that actually mean? So that means that essentially P is moving backwards and forwards like that. So as we move P back and forth, the energy transfer goes along the spring like so. Now your first job is to label a rarefaction on figure 1a. So the way we can see this spring set up is that we can see these regions here that are compressed, and these are what we call compressions, and then we can see these spaced out regions, and these here are your rarefactions. So just something, it's like a small circle just for that. We'll cover that particular question perfectly well. Okay, now the next thing it's going to ask to do, so give the wavelength of the longitudinal wave in the slinky spring and use the ruler here. So what I would suggest you do here, rather than trying to measure a wavelength here to here, say, is just start from the back of the wave. So take this as your starting point. So this is the start of the wave at 0. And then what you can see is you've got 3 of these little wave patterns before you hit a compression. So if you count back from this compression, 1, 2, 3, then the wave kind of starts or ends there. All right, that takes you to about there. Okay, and we'll just measure that section. Okay, so from there to there, that each of these little increments is 2. So this is 30, 32, about 33 millimeters, like so. So the answer just down here is 33 millimeters. Excellent. Okay. Now the next job, bit of a strange thing there, never mind, is to describe how a longitudinal wave is produced on a slinky spring. Now what we said back here is that we've got this movement either backwards and forwards, push and pull, whatever you want to describe it as in that particular respect. And then this causes the energy transfer to move along. Now the key word here is parallel, which is not quite what you can see there. Parallel, there you go. Okay, so what we're going to do in here, I'm just going to type in a little box here. We're going to say that P is essentially moved back and forth, or you could say pushed and pulled. And what this does then is this generates a wave that transfers energy from P to Q, and the key word then is parallel to the source. Okay, so that's the really important thing there, is that we understand the idea that you've got that movement back and forth at P here, and then that creates this energy transfer parallel to that. And that picks up your 2 marks. It's one for basically saying back and forth, and then it's the other for saying the kind of parallel bit, parallel to the direction of the wave. Then we come to this wave. Now what they're doing in this wave is they're basically turning the wave into a transverse wave. So you can see that you've got this up and down motion like so, and it asks you to show the amplitude. Okay, so the amplitude in this particular case, let's just think about what that actually means. If we turn this into a wave like so, there's your wave and your rest point along here. Now this A is, you might be tempted to go for A because it's an up and, the amplitude is measured up and down, but this actually tells you the maximum and the minimum displacements. Okay, so the amplitude, remember, is just half of that from the rest point. So this is the rest point to the peak or the trough. So it could be measured here as well. Okay, so C is the answer to that one. Okay, that's good. Now this second question, so this goes into emission spectra. We did a bit of work on this in revision, but this really pulls on that. And now it's got 4 different gases. So you've got A, B, C, and D. And it tells you that neon has 2 spectral lines that are about 10 nanometers apart. So what this tells you is they're really close together. Okay, so what you want to be looking for here is lines that look like this one, or this one, or perhaps it could be this one. Now, these spectral lines are at the red end of the spectrum. So just go straight up here and go, look, well, we've got red and we've got blue. So it must be at this end of the spectrum. Okay. So the next thing that we can then start to think about is which of the emission spectrum is neon. Okay, so it must be at this end. So we're looking for two spectral lines close together. And I think most of you can see that those two there are pretty close together in that sense. So we're going to go for C, and C will get you the mark on that one. Again, that's just another really quick, easy mark. If you've done your revision on this, then you should be comfortable when picking this up. Now, this one here, this question starts to get you thinking about how we apply this. So it looks at light from a star. Okay, so here's your light from a star spectrum. And then you've got some elements here that could be in that star. And it asks you to justify which of the elements P, Q, R, or S are found in the star spectrum. Okay, and you may add, so what it means by you may add to figure 4 is you can draw lines all over it. So what you're going to do straight away, and this is the way I would do this, is go, right, well, that one lines up with that one lines up with that one, and just draw straight lines all the way down through. That one lines up with that one. The minute you start getting some kind of matchup like this, you should immediately be thinking, well, that must mean that R is found inside this star. Okay. Now, but what this means actually, when you start to work this through, is not all of these lines have necessarily been picked up. Like, look at this one. This one's not been picked up. This one here and this one here. Now, what you then do is just work your way through the other elements. So it's not going to be P, because P doesn't match up. Look, there's no match up there, but we can see that Q does match up. So you've got match up there, you've got a match up there, you've got a match there, and you've got a match there. So this tells you that Q and R. So Q and R, just let that load, are found within the star. Now that gets you 2 of the marks. Now this is worth 3 marks. So where are you going to get that extra mark from? You might, if you get a generous marker, get it from that, just drawing those lines. But the key thing is using the word match. And what we mean by that is that the spectral lines match up. Okay, so make sure, that is an awful way of spelling the word match, but you get the idea. So there's match up between Q and R and the star spectrum. And it's that gets you that 3rd mark. Okay, let's just scroll down and see where we get to next. So the next thing, we start to talk about diffraction gratings. The diffraction grating produces a bright line on the screen. So that's kind of important. So what you've got to think back to here is where we started looking through diffraction gratings. We put the laser through, and the laser gave us like these, you remember we got those shapes where you got like dark regions and bright regions like that, and it gave you a pattern. Okay, and what you've got to think about is what's happening in these regions where you've got a spot, and what happens here. Okay, because that's going to help you to get your head around the answer to this. The distance traveled from the diffraction grating to the screen is different for each ray of light. So this one travels less far than this one, which travels less far than this one. Okay, and this is called path difference. And we talked about path difference when we did a bit of work around the we had some ripples like that, like so, and the ripples essentially started to cross over, and it's that gave us this pattern. Now, what it's then asking you to do, it seems really, it's quite hard for just 1 mark to work this one out, but which path difference between the rays of light gives the bright line? So there's got to be a bright point here. So what that means is that we must be getting constructive. So let's just write that a bit slower, sorry. So that's got to be let's just write that again above, sorry guys. Constructive. This is awfully slow. Sorry about that, guys. Okay, so constructive. So what that means is that we have to be getting peaks and troughs at the same time. Now, the only way you're ever going to get that in this particular case is if you have 1 wavelength apart. So if we think about this diagrammatically, okay, so just draw a diagram there. Let's just change the color to something like that. So if we have a wave that's doing that, like so. Again, that's a pretty awful diagram, but you get the idea in a minute when I just add my next color, say if it's green. if they are one wavelength apart, then the next wavelength essentially is going to have the same pattern like that. And what this actually means is that all of these here are coherent. Let's type that in rather than try and write it. Okay, so they're coherent. And because they're coherent, that means that their wavelengths match up in that particular sense. Okay, and that's what gives you that constructive interference pattern on the wall. Okay, so again, 1 mark for quite a hard answer in that particular respect. Now, mobile phones come up in this next one, and I love how they give you this image of a mobile phone with no network, just in case you've never seen what one of those looks like before. So it says here, there are places where mobile phone signals cannot be received when the user is in range of a transmitter. So there's a number of different ways you can get the marks on this one, and it is a 2-mark question. The one thing that really gets me on this one is I think about, when do you most experience no network? And actually, I tend to find that isn't really to do with where I am. Okay, it's more to do with how many other people are around me trying to use the network. So if ever you go to a really big event, not that that's going to happen at the moment, but if you ever went to a big event, what that actually means is that you generally have too many users in that particular respect. So what that means essentially is there are too few frequencies available. So too many users, and this leads to lack of available frequencies. So actually, the first answer that I'm giving you there, it doesn't actually relate to the waves as much as it really just relates to the fact that, too many people are trying to use the network in that particular respect. Now, the obvious one, the one that most of you went for, is this idea that you're at the bottom of a large building, or you're underground. So we kind of put that one, so underground, inside a large building in that particular respect. So you've got that kind of idea. Now, what this leads to, what's really important is, don't use the word interference. Interference doesn't come into play when this is the case. What this is about really is about absorption of the signal, or a reduction in the signal intensity. Okay, so that signal's dropped so far down that essentially it's not reaching the level at which you need in order to perform a phone call or a message or whatever it is. Now, it's possible you do get interference, but interference tends to come from reflection of signals from essentially large buildings. So it's possible in some respects that if you, or a hill can do the same. So the reflection of a signal, what that actually leads to is destructive interference. So if you're going to talk about interference in this particular case, what it actually means is you need to think about the fact that waves are coming in alongside all the waves that are coming from the mast. So there's a number of different ways that you can pick up 2 marks here, and they're all acceptable in that particular respect. Okay, so that's essentially 6 marks there, but you can't get 6 marks because obviously it's a 2-mark question in that respect. So let's just have a look at the mark scheme with that one and try and make sure you understand each one. The key thing here is just explaining. So you're stating here too many users, so there's a problem, and then how that impacts upon. So there's lack of available frequencies at which you can actually attach to that network. Now, this next question, this one requires a calculator unless you're very, very good at arithmetics in that particular respect. So let's just make sure we're comfortable with that idea. So this uses the equation k equals r squared. So I equals k divided by r squared. So I'm just going to change my color pen back to blue. So what we need to do in this case is we need to work out what actually are we going to be working with, and what do we actually need to put into an equation. So the first thing that we need to do really, I think, is just work out, what is I. So once we've got what I is, now I is, in this particular case, the intensity of the light that we're trying to get to. Okay, so this is 9.0 times 9.0. Sorry, that should be times this 10 to the minus 10. Okay, that's really not keeping up with me there, but never mind. And then your K, I'm just going to type this one in instead, guys. K is equal to 1.8. So that 1.8 is coming from here. So it actually tells you, in this case, the power given by the constant is K, 1.8. So it tells you what K is in that respect. So what it's asking you to do essentially is to calculate the distance, isn't it? So R is the distance. So in this case, what you're going to do is you're going to basically put R at the beginning of your formula. Okay, so in this particular case, R is equal to the square root. And if we rearrange this formula, so we definitely need the square root because we need to move this squared over. But when we do that, and this is going to be essentially K divided by I in this particular case. So that is equal to essentially what you're going to do is you're going to do 1.8 divided by 9 times 10 to the power minus 10, and then you can square root it. Okay, so just make sure you're kind of capable of doing that. So you put it into your calculator. What it will give you essentially is something along the lines of 45,000, and that will be in meters. Okay, so yep, that's worked well, hasn't it? So 45, 0, 0, and that's in meters. And then you just need to basically divide by 1,000. Okay, so divide it by 1,000. So, and it gives you something like, well, it will give you exactly 45 kilometers in that particular respect. Okay, so and that's not looking like 45 at all, is it? So your answer is 45 kilometers. Okay, and again, you've got the mark scheme for this, so just have a look back through, make sure you know where these answers have come from, be comfortable with that aspect. Now this question here gets you thinking about Bluetooth and Wi-Fi, and we did a session on Bluetooth, which is good news, and they love questions on Bluetooth, and it just asks you basically to give one reason why Bluetooth signal does not interfere with Wi-Fi signal. And there's one really easy answer to this. Okay, so remember that we talked about the fact that Bluetooth frequency hops. Let's spell that right. Frequency hopping. So if you kind of understand that idea, there's all sorts of really complex answers for this, but the key thing here is it's just a single thing that you understand the fact that Bluetooth jumps frequency constantly, whereas Wi-Fi uses a set frequency band. And because what Bluetooth constantly changes frequency, it doesn't interfere as easily with Wi-Fi signal. This question here, this gets you thinking about useful applications of Bluetooth. Here, what I'm getting at really is, you think about, we talk about Fitbit, we talk about heart rate monitors, linking to fitness apps on a phone. Yeah, so the key thing there is you're not just stating like, oh yeah, you can transfer something from here to here. It's about thinking about specific useful applications. Okay, so car tether to phone in that respect. So some cars do that. You could talk about like hands-free things where you can have a headphone. You can talk about headphones. In that respect, you can talk about some garage doors. You're talking like really posh things there, aren't you? Like things that nice, expensive garage doors that open by a remote inside a car or inside a phone. You can literally go anywhere with that, but you need to be specific to get those 2 marks in that particular respect. So that answers that question. Let's move down to the next one. So this one, again, is another maths-based question. What it does in this particular respect is it gives you the formula. They're really nice in this one. They give you the formula sheet at the end, but they give you the formulas you need to use. In this particular respect, we're given the value for n, and we need to calculate the critical angle. Now, what you need to remember is you can't use this formula, this base formula, in its base form. Okay, so it's not. What you've got to do is you've got to take that sign and stick it over here. Okay, so that makes it basically C is equal to, let's just let that catch up. C is equal to sine to the -1. So hopefully this is coming back to you now of 1 over n. Okay, so stick that in. So there's your n, and 1 stays as 1. So it's 1 divided by 1.52, and then you do the inverse sine of that, and it will give you an answer of somewhere around 41.1. Okay, so it's really important that your answer there rounds down to 41.11. So it's not 41.6, for example, and that is your answer down there. Okay, so again, if you're not sure about where that answer has come from, you just need to revise this topic and look back. It gives you all the bits you need to know. So that the only thing I probably should add there is that 1.52 is what goes in there on that n. So it's 1 divided by that, and then sine -1 of that. So again, that's three marks there, 3 nice easy marks in that particular respect. Okay, so this one, it talks about total internal reflection, and you've got a cladded wire and a non-cladded fiber, and it just gets you thinking about one advantage of transmitting with cladding. So it's this one here. What's the advantage of this? Now this is the same length of cable. And what you'll hopefully notice, so here, 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 and here, we have 4 reflection points. So 1, 2, 3, 4. This one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 reflection points all the way along that. Now, every time the light reflects or bounces back off this, you get energy loss. Okay. I'm not going to write that because you can't see it anyway, but you get energy loss. So that's one of the first things to note straight away. So what some of the possible answers, but the first thing we need to think about is, why is this the case? Okay, so again, if we draw in here, that's our normal. Okay, that angle there is much, much greater than the angle there. Okay, now that angle is C. C is bigger, it's greater. Okay, so critical angle is greater with cladding. Then you've got to say what that means. So this means that the light reflects at a larger angle, and therefore reflects off the boundary less. Okay, this reduces energy loss in that particular respect, energy and energy loss or data loss in that respect. So it's basically identifying something as an advantage and then saying why it's an advantage. What you could kind of argue in this particular respect is that the distance traveled is less. So less distance traveled. If you counted up, if you measured, the distance over an entire wire, this one travels further than this one. Because you've got less distance traveled over the same amount of time, what you will then find is transmission is faster. Don't be tempted at this point to say that the wave is traveling faster, because the wave travels at the same speed in either case. It's just that from the destination to the source to the destination, it's faster with the cladding, and that can get you your 2 marks for that. There are some other answers in the mock in the mark scheme, but do have a look at that. And then we come to this last question. It doesn't take us too long to work through this, but you might find that sometimes you might take longer to work through some answers. Okay, so the first thing to note here then is it asks you to basically talk about compare the waves. So the first thing to note is what you should do if it's asking you to compare is do similarities and differences. That's the kind of first thing that you need to do here. So do think about it like that. So what are the similarities? I can't spell, which is no news to most of you. I think you've noticed that about some of my writing. I can't spell. So similarities, what you might consider in this respect is that both use essentially vibrations or oscillations. That's nothing new. We're talking about waves at the end of the day. They both require stationary wave formations in terms of both, stringed and piped music. Both of them essentially produce sound due to resonance. So you can start to see there are a couple of similarities in this respect. So that's what that bit is getting at. Okay, so that section, and again, you might find so the similarities are these things here. Okay, so let's have a look at some of the differences. Well, what we might say straight away then is that a string with a string, it requires a string. Oh, let's spell that right. String to vibrate. Whereas with the air column, it is the air particles to vibrate. Okay. Seems obvious, but it's a key difference between the two. One uses a solid string and the other is using air particles in a gas. Now the wave itself it essentially sets up a transverse. So wave is transverse in a string, whereas the wave is longitudinal in an air column. And that's another key difference. The other key difference really then comes from how you might go about drawing these particular waves. So in this particular case, what you might do is you might draw a wave pattern for a string like that, and you'll end up with, you can go, oh, it's got a node at this end, and it's got a node at this end, and it's got an antinode. And what you might say about a string is that it starts and ends on a node with an antinode in the middle in that respect. Whereas your open air column, generally speaking, does that. So you have at one end an antinode and then a node in the middle. This isn't writing particularly well at the moment, unfortunately. And then you have an antinode at this end, okay, like that. And it's just making sure you can kind of compare the differences between the two. So drawing diagrams is definitely encouraged for this. If anything about harmonics comes up, draw the diagrams for the harmonics, okay? So we'll add that there like that. So harmonic. No, it's not typing, is it? There we go. Harmonic diagrams. Definitely add those in. Make sure you revise them. And then it's just making sure you kind of talk about, maybe you might talk about the fundamental, the first, second, third harmonics. Draw diagrams again. Note the key differences. If you're really going to push this to a distinction, what you might start to then do is talk about wavelength. So wavelength, and you might relate this to degrees and radians, which we did. We did this in the lesson, and we talked about the fact that this is half a wave. So therefore, if it's half a wave, then it's pi. So computer's just completely going weird there. Never mind. Yeah. So just that idea that you've got half a wave, which is pi in radians, and it's 180 degrees. And then when you go to the next one, it's 2 pi 360 degrees, and how that goes on. And so that's how you can kind of hit that 6 mark bit. So just making sure there that you, with these 6 mark questions, is read the command word. So here it says compare the types of waveformed. So it's making sure that you're comparing the similarities and differences in that respect. And they like questions like this where you compare. Now that leads us to the end of that. So you've got the mark schemes, hopefully. I'm going to sign off now, and I'll do more of these if they're of any use to you. So all the best. Have a good rest of the day.